Hi everyone, I am Dr. Kiran, working as an assistant professor in the Department of Electronics and Communication Engineering, MLR Institute of Technology, Hyderabad, India. Today we are going to study what is FWR rectifier. So these are the today's topics. We will cover what is FWR rectifier and its operation, and what are the performance parameters of FWR rectifier, and conclude with summary. So first, what is FWR rectifier? So it required two diodes to construct this FWR rectifier, and it utilizes two complete cycles of the input signal. So this is your input signal. So we have two cycles, positive cycle and negative half cycle. Okay. So if you apply this input signal here, so it utilizes completely the full cycle of the input signal. So what are the two different types of FWR rectifiers are depending upon the transformer. So we have center tapped FWR rectifier and bridge rectifier. So we mainly concentrate on these two types. So first, so this is the circuit diagram for full wave center tapped FWR rectifier circuit, and this is your transformer, and here across the transformer terminals you are applying V input, that is the signal. So if you apply during positive half cycle, what happens at this point, this terminal got positive, and as we know, when positive is connected to anode of the battery, then the diode gets forward bias. So during negative half cycle, what happens, this terminal gets negative, so negative is connected to positive of the battery, so positive of the diode, then it is called reverse bias. So during positive half cycle, diode D1 gets forward bias. During negative half cycle, diode D2 gets forward bias. Okay. So therefore, both the cycles are utilized properly. So 0 to pi positive half cycle and pi to 2 pi is the negative half cycle. So during positive half cycle, diode D1 conducts through RL, and at the same time, so the current will flow like this, and at the same time during negative half cycle, this terminal will get negative and this terminal gets positive. So positive connected to positive of the anode of the diode, then it is gets forward bias. So during positive half cycle, negative half cycle, the diode D2 gets forward bias and D1 gets reverse bias. So due to this, for the both half cycles, so during positive half cycle, so you will find the output voltage, and during negative half cycle also you will get the voltage. So therefore, so this is Vm is the peak voltage, maximum voltage. So therefore, this is the input output waveforms. So this is our basic operation of a FWR rectifier, center tapped FWR rectifier. So which requires two diodes. Okay. So let us see what are the different parameters, performance parameters of FWR rectifier. So average DC load current, average DC load voltage, RMS load current, DC output power, AC input power, efficiency, ripple factor, peak inverse voltage PIV, transformer utilization factor TUF, voltage regulation, form factor and peak factor. So these are the few parameters of FWR rectifier. So let us see one by one. So average DC load current. What do you mean by average DC load current? That is IDC or I average. So DC parameter. Mathematically, the current waveform can be described as I is equal to Im sin omega t, we know. So I is equal to Im sin omega t. So this is the input signal. So this is, let us say, Im. This is I. So Im, and this is minus Im, of course. Okay, so this is omega t. So during 0 to 2 pi, so the output current through the rectified output current through the full wave rectifier is represented with this IL is equal to Im sin omega t during 0 to 2 pi, because the output is like this. So 0 to pi and 2 pi. So therefore we can write this, the limits are 0 to 2 pi. So therefore where Im is the peak current or maximum current. So in order to calculate DC or average current through the full wave rectifier, we can write this 1 upon pi 0 to pi IL d omega t. So because 1 pi, because we have considered only one cycle, because both are same for both half cycles. During positive half cycle diode D1 conducts, during negative half cycle diode D2 conducts. So both we have to consider. So therefore 0 to pi IL d omega t, that is 1 by pi 0 to pi Im sin omega t. What is IL? IL is Im sin omega t. So if you substitute values, so we can write this as Im can be taken out. So In upon pi, so integral sin omega d omega t is minus cos omega t, and this is, so we can take it out, this minus sign. So minus Im by pi cos pi minus cos 0. So cos pi value is minus 1 minus cos 0 value is plus 1. So minus into plus 1 will be minus 1. So minus 1 gets minus 2. So the minus 2 and this will be plus 2. So minus 2 into minus, already minus is there in front. So it will be 2 Im by pi. So that is the I average of the forward current. Similarly, next parameter is average DC load voltage, VDC. So how to calculate this? Similar to we know, according to Ohm's law, V is equal to IR. So here we want VDC. So VDC is equal to IDC into RL. So what is IDC? Just now we have calculated 2 Im by pi into RL. So 2 Im into RL by pi. So we know that V is equal to IR. Vm is equal to Im into RL. You can write. So Im into RL, in place of Im into RL, I can write Vm. So therefore, V average or VDC can be written as 2 Vm by pi. I average or IDC is 2 Im by pi, and V average or VDC is equal to this one, 2 Vm by pi. Simple to remember. And now here we have Im. Here we have to consider secondary coil resistance, forward resistance of the diode, and load resistance. All the three resistances are given. So while doing numerical problems, you have to consider whether they are given, we are given this forward resistance or secondary resistance, all those things. Okay, otherwise you don't consider. So RS is the resistance of the secondary coil winding of the transformer, RF is the forward resistance of the diode, and RL is the load resistance. And one important point here is RL always large compared to RS and RF. So RL always greater than RS plus RF. So sometimes while doing numerical problems, you can utilize this. So sometimes you can neglect this when compared with the RL. So RL has got high value or large value. The next one, RMS load current, IRMS. So you know root mean square. IRMS means root mean square. So how to calculate root mean square value? So squaring, finding the mean and applying square root. So applying square root means this one, square root of 1 upon pi 0 to pi Im sin omega t square, squaring, finding mean. Mean means upon pi. So 0 to pi m sin omega t whole square into d omega t. So Im can be written outside because Im square it is square Im square. So Im square, when take it outside, it becomes Im. So root 1 upon pi 1 minus what is sine square omega t? Integral 0 to pi sine square omega t value is 1 minus cos 2 omega t by 2. So therefore, so we have a Im 1 by pi. So here 1 by 2, that is 0 to integral 0 to pi. So if you integrate this 0 to pi, here integrate 0 to pi by 1 by 2, integral 1 by 2 d omega t. So integral 0 to pi 1 by 2 d omega t becomes, so it is t by 2 means, so pi by 2 we can write. So here 1 by pi and this is pi. So pi gets cancelled. So finally you will get 1 by root 2. So Im by root 2. Okay. So this is IRMS value, Im by root 2. Or similarly, so we can also calculate this VRMS is equal to Vm by root 2. So easy to remember. Next parameter is DC output power. So what is DC output power? So PDC is equal to VDC into IDC or VDC square by RL. So what is VDC? We know 2 Vm by pi. So if you substitute these values, so you will get what is the value of PDC? 4 Vm square by RL into pi square. So similar to this, AC input power. So this is DC output power means PDC means what? Power delivered to the load. This is AC input power. Okay. So it is IRM square into this one. So of course we can neglect this while doing problems. So whether you in the numerical problem, if you are given these values, you have to consider. So otherwise you can neglect. So here for the time being, I have neglected this. So I can write VRMS square by RL, and PAC is equal to Im square by, because IRMS is equal to Im by 2. So Im square by 4. So RS plus RF plus RL. So I can directly write Vm square by 2 RL. And efficiency is what? So what is efficiency? Efficiency is eta is equal to PDC upon PAC. So PDC is 8, and so if you solve for this, so what is PDC? This value. So if you substitute here 4 Vm square by RL pi square upon PAC is Vm square by 2 RL. So RL gets cancelled. If you keep this 2, then it will be 8 pi square. M square gets cancelled. So it will be 8 pi square. So what is the value of this 8 pi square is 8.812. So if you consider percentage, so in percentage the efficiency is 81.2%. This is the very good value. That means 81.2 is the efficiency of full wave rectifier, whereas in case of half wave rectifier it is just 40%. So here 80% means 80% of the power is utilized, or rectification is good in this full wave rectifier. Now ripple factor. So what do you mean by ripple factor? We have studied in the previous sessions. So ripple factor means, so what are the unwanted components, AC components present in the rectified output? It can be specified by this ripple factor. So it is the ratio of RMS value of AC component to the DC value component. So what is RMS value of AC component? Means VRRMS, and VRRMS is given by root of VRMS square minus VDC square. And if you divide with VDC through this expression, then ripple factor is root of VRMS square by VDC whole square minus 1. So RMS value of the voltage at the load resistance is approximately equal to VRMS is equals to under root 1 upon pi 0 to pi Vm square sine square omega t d omega t. So if you solve for this, you will get Vm by root 2 is the VRMS. Of course, we know Vm is equal to root 2 into VRMS. So this is the standard form. So therefore, the ripple factor of this full wave rectifier, after calculating the ripple values, so the value is 0.482 is the ripple. That means approximately 48% ripples present in the rectified output. So this indicates 48% is ripples present, that is AC component present in the rectified output of the full wave rectifier. So whereas in case of half wave rectifier it is approximately 121%. So 121% ripples are there in the half wave rectifier rectified output. So whereas in this case we have only in full wave rectifier 48% only. So remaining DC component. So peak inverse voltage. 8th parameter is peak inverse voltage. The peak inverse voltage for a full wave rectifier is 2 Vm. So twice the peak voltage, because secondary voltage appears across the non-conducting diode. So that is why we have a 2 Vm is the peak inverse voltage, the maximum voltage that the diode can withstand is called peak inverse voltage. And transformer utilization factor. So the average transformer utilization factor of a full wave rectifier circuit is determined by considering the primary and secondary windings separately. So and its value, if you solve for this, we will get a 0.693 as the TUF value, transformer utilization factor. So 0.693 is the good value. So that's why full wave rectifier has greater advantage compared to the half wave rectifier. Next, form factor. So what is mean by form factor? So it is the ratio of RMS value of the output voltage and average value of the output voltage. So we know that RMS value of the output voltage is Vm by root 2 and average value is 2 Vm by pi. Just now we have discussed, and that is pi upon root 2 and the form factor value is 1.11, good value. And next parameter is peak factor. Peak factor means peak value of the output voltage upon RMS value of the output voltage. So what is the peak value? We have Vm. And what is the RMS value? Vm by root 2. So Vm gets cancelled. Finally you will get 1.41. That is root 2 is the peak factor. So form factor and peak factors are good values for full wave rectifier. So next is bridge rectifier. So another type of the full wave rectifier is bridge rectifier. The basic difference between center tapped and the bridge rectifier is, in full wave rectifier 2 diodes are used, in bridge rectifier 4 diodes are used. Remaining the performance parameters all are same except peak inverse voltage, and few advantages are there with the bridge rectifier, using bridge rectifier compared to the full wave rectifier, center tapped full wave rectifiers. Actually the basic disadvantage with the center tapped full wave rectifier is bulky. The center tapped transformer is bulky. So whereas that is compared to 4 diodes, using 4 diodes it is bulky while using center tapped transformer. So this is advantage of full bridge rectifier. Same, it is made with the 4 diodes here, D1, D2, D3, D4, and utilizes 2 cycles, same operation with the full wave rectifier, center tapped. So here during positive half cycle of the input signal, AC input, D1, D3 conducts. So because at this point during positive half cycle, at this point will get more positive, and that means positive is connected to anode. So this is anode and this is also anode. So therefore both D1, D3 gets forward bias. During positive half cycle, D1 and D2 gets forward bias. Sorry, D1 and D3. And during negative half cycle, next half cycle, D2 and D4 gets forward bias. Okay, so when D1, D3 forward bias means whatever the supply we have, so that is available at the across the load resistance. So that is plus VM. During negative half cycle also same. So D4 and D2, D4 gets forward bias, therefore you will get the output voltage across the load resistor. So this is the basic operation and input output waveforms of a bridge rectifier. So the basic advantage of bridge rectifier, so as I just now told you that the center tap transformer is bulky, so therefore this is the disadvantage of center tapped. And then the PIV across either of the non-conducting diodes is VM, so PIV is decreased. So whereas in this center tapped, the PIV is 2 VM. Now the transformer utilization factor is considerably high for bridge rectifier, that is 0.812. Okay, so whereas transformer utilization for center tapped, it is 0.69 something, 69%, and here it is 81%. So this is the advantage, it counts, and used in the applications allowing floating output terminals. Floating output terminals means no terminal is grounded, so that is the floating input output terminals. So in such applications we can better use this bridge rectifier. Okay, so that's all for today's session. So what we have covered so far, we have discussed what is full wave rectifier and its operation, input output waveforms, and we have discussed what is center tapped full wave rectifier and performance parameters of the center tapped full wave rectifier, and we have discussed what is bridge rectifier and what is the difference between bridge rectifier and the center tapped rectifier, and so what are the advantage and what is the comparison TUF in case of TUF and PIV. Okay, that's all for today's session, and next topic will be on filters. Thank you very much.